Hello everybody, how are you? Just realized I should adjust my volume or else we're going to get feedback. Okay, great. Happy Friday, and I hope that you had a very interesting week this week. It's a pleasure to be able to talk to everybody about math. And if you're new to this live stream, just as a welcome, we're going to have a discussion about all kinds of different topics. Now, these topics are going to be inspired by you. I like to have the opportunity to go and see what people are interested in. And then we will go and look at what directions you're interested in and try to make up some improvisational math lessons on the spot. And if you're new, you'll notice this is very different from your normal math class, but that's because you already have math class with your teacher at school, and I'm not looking to replace them. They're probably already doing a very good job. Instead, I'm trying to give you something that you probably can't find as easily in a textbook. If you have been here before, I see that you are already talking about the color of the shirt. And so I suppose that means that you know that there are a lot of these inside jokes that will come along. In some sense, by doing this live stream, we've also made a wonderful little community here, which always has people coming together every single day, basically every 24 hours, to go and talk about some interesting questions. So what will we talk about today? Let's find out. So I'm looking at all of these. Oh yes, somebody said white pixel in top right corner. Do you know what that white pixel is? I can tell you what that white pixel is if you're kind of curious. So that white pixel is actually the mouse cursor. So some of you may have noticed that somehow whenever I start, there's always a white pixel up there. The reason that's there is because that's actually where the button is for me to press start recording. But of course, if I want to move that pixel around, I can just do something like this and it's gone. Okay, and in general, I mean, all of these things have reasons. One of the reasons I love working with computers is because whenever you do something, there's a real reason why it happened. And math is the same. Somehow, if you understand math, you're used to finding the real reason underneath, and then you can go and figure out, why is something wrong with your computer. Aha. Let's see. What do we have here? Oh, interesting. So I'm going to start with something that's a more general question, just because I see one that has come already. It's from somebody who says, I love mathematics, but my marks are poor, meaning I assume that the grades are not as good at school, but you love mathematics. Good for you. That means that you'll have a long way to go. A long way to go means that you can go and do lots of great things. Of course, do your best in school. That's an important thing to do. But if you love a subject and you keep learning it, you will most likely learn even more than what was ever taught in school. So although it may be the case that your school grades are not as high, hopefully your understanding of math is higher. And certainly by talking with us about this kind of crazy math every single day, hopefully you'll learn a bunch of things that are even like different directions than what you normally see in the school. What else do we have here? Okay. So I see that somebody has said, could you explain, Luka Nedimovic says, hello, hope you are well. Could you explain from the start one interesting graph problem? Now this is an interesting question in my opinion, because I don't know what you mean by graph. In fact, there are a lot of graphs that people are used to. A lot of times, people are used to thinking of a graph like this. You take two axes, and you graph, for example, y equals x plus 1. So this is an example of a graph. That's fine. But unfortunately, I don't think this is exactly what the person asking the question was curious about, because there's another kind of graph also. Another kind of graph is something that's talking about a network. So here's an interesting graph problem about a different kind of graph. A different kind of graph is one where you could imagine that there were a bunch of people. So all these people, I guess, had come to a party. I guess this is before COVID-19, before social distancing. There were just all these people at the party. And each of the people, some of them shook hands. Again, something that we don't do anymore these days. Like maybe those two shook hands. And we have all these different handshakes. And each person kept track of how many handshakes that they made. This person said they shook two hands, two handshakes, two shakes. I guess it looks like milkshakes or something, but no, it's handshakes, two shakes, two handshakes. Over here, this person took one handshake. This person took one handshake. And this person took 0 handshakes. So that's just one example. One example is if I just told you that there were these 4 people and this is what happened. That person shook that one's hand, that one shook that one's hand, this one didn't shake anyone's hand. You could say, okay, great, I've got all of these different numbers of handshakes that each person has taken. No, handshaking is bad. You're right, and Tiger Lee is talking about milkshakes. I guess in social distancing world, we just have milkshakes, not handshakes. But now, suppose this is the number of handshakes that each person had. That's nice. But an interesting graph problem, one of the first ones that I learned when I was learning about graph theory, was that you can actually know something very interesting about the number of handshakes, about the sum of the numbers of handshakes that each person took. For example, over here there are 2 handshakes, there's 1 handshake, there's 1 handshake, and there's 0 handshakes. And look what happens if I add them all together. 2 plus 1 plus 1 plus 0, that is 4. Okay, let's do this again. Let's do this with a more complicated picture. Let's suppose that now, I'm not going to draw the people like just people anymore. The people are dots. And this is an example of a graph. The people don't even have to be standing in a circle. Just something like this. These are people. Each of those is a person. And also, there's a whole bunch of random handshakes that are happening. Maybe this person loves to shake hands. And maybe these people shake hands with each other. Something simple. Maybe I can even do something like this. So let's pretend that this is what happened at the party. Now let's go and count. Yeah, these are random people randomly shaking hands. And let's count how many handshakes did we have for each person. This person shook 1 hand. This person shook 1 hand. This person shook 2 hands. This person shook 2 hands. This one was 2. No, it wasn't. I can't count. This person was 3. And this person shook 1. And let's go and add up all those numbers again just for fun. What are we talking about, Nathan Chan? We're talking about the patterns that happen when you shake hands, when you have a bunch of people shaking hands. And I'm just going to count for each person how many hands did they shake. And let's go and add these up. 1 plus 1 plus 2 plus 2 plus 3 plus 1. Oh, what is this? Help me, guys. 6. Looks like 10. Maybe it's 10. Neat. So we can have all of these different things, like somehow, oh yes, Grace Yan says I can't count equals me every day. Right, and I sympathize with you. Somehow counting is not the most interesting thing in the world. And so sometimes if your brain is thinking about something else, your counting will not be the most accurate. But we got 10. Okay, how nice. Now I'm going to tell you, there was this other party. In this other party, there were these people. Oh, there was a whole ton of people. Whole ton of people in this party. Oops, those aren't dots. All these people in this party, and I didn't keep track of who shook hands with who. I just know how many hands they shook. This one shook 2, this one shook 4, this one shook 8 hands. Actually, that can't be. There aren't 8 people here. This one shook 6 hands, and here was a 1 and a 3, and another 3, and this one shook 2 hands, and this shook 0 hands. So here's a party, and I'm just telling you that these people kept track of how many hands that they shook. So each of these people, this person says, they shook 1 person's hand. This person shook 3 people's hands. This person shook 3 people's hands. And then this person shook 6 people's hands, and so on. So, these people are telling me after the party that these are how many hands they shook. What do you think? Does it seem reasonable? Maybe we can just try to draw. Let's try to figure out what actually happened at this party. Let's try to figure out what happened at this party. Who shook hands with who? Well, I know about the 0. 0 didn't shake hands with anyone, so that's easy. And 6, I guess I have to figure out which 6 people did the 6. Oh my, it seems really hard. But I see that there are some people here in the chat who already know that something is deeply, deeply wrong. So it turns out this is impossible. They're lying. Well, maybe lying is the wrong word. We don't intentionally. Maybe people are like me. They just can't count. Yes, that's what we should say. They can't count. Right? They just can't count. There's something wrong here. They can't count. And why is it not possible? The reason it's not possible is, let's add up all the numbers. And if you add up all the numbers, what is it? 2 plus 4. Let's put a 0 in front. 0 plus 2 plus 4. Then it's sort of like left to right. 0 plus 2 plus 4 plus 6 plus 3 plus 2 plus 3 plus 1. And if I can't count, adding is even harder. So what is this? I guess that's like 10, so that's 12, 15, 17, 20, Did I do that right? Is it 21? I saw some people saying it was 23. So that means I either can't count or I can't write or I can't add or some combination of the whole thing. Oh, but it looks like people seem to agree it's 21. So we'll say 21. Now, why is 21 bad? 21 is odd. You see, if you notice the pattern, the previous ones, the sums were all even. And why? Let's go back. Here's an example. 2 plus 1 is 4. And 4 is even. That's nice. Let's go to the next one. The next one, I got 10, and 10 is even. That's nice. But what's the relationship, actually, between the number and the graph or the picture? Some people may have noticed, maybe you've seen this before, or maybe you've noticed a pattern. This says 10, and 10 is 2 times 5. And here's a graph. Is there anything that's 5 about this? If you look at this picture of like the people who shook hands with who, is there anything about that picture that screams 5 at you? Temp ID, thank you. There are 5 connections. You see, 1, 2, 3, 4, 5. There are 5 connections. That's nice. So it looks like it's 2 times the number of connections. How about this? 4. 4 is also 2 times the number of connections. The number of connections here was 2. And why is that? It's because for every connection gives you +1 to each person, right? So there's this connection here. That's a handshake. So the hands met. And when you have a handshake, this person gets +1, and this person gets +1 also. So that makes perfect sense. For each of the handshakes, you get +1 to both people. And here's another handshake, +1 to both people. And in the end, if you look at your score, you have this +1, and that was 2. And this just +1, that's a 1. And this +1, that's a 1. So that's it. All that's going on is that this sum of the number of handshakes that every single person took is just going to be exactly double of how many connections there were at all. If you look here, same thing happens. For example, this guy counts 3, but that's because this one gave 1, this one gave 1, and this one gave 1. So 1 plus 1 plus 1 is 3. And that's why the answer is always going to be 2 times the number of connections. So then what happened here? Well, then this is just wrong, because you cannot possibly have 2 times the number of connections be equal to 21. 21 is an odd number. So presumably what happened is that somebody tried to do this, and the other person just didn't shake their hand. Well, what that means is that person didn't count it properly. That's not what we were trying to use here. We weren't allowing that to be going on in this problem. But okay, so to me, this is an example of a fun problem in graph theory. It's a fun early problem in graph theory. If you have never learned this subject before, it's really nifty. You can do lots and lots and lots where you just go and think about what happens when you have dots for people and connections whenever those people have met or shaken hands or something. And that actually is the fundamental insight behind Novid, which is the app that we're building to try to help stop this COVID-19. Let's see, what else can we talk about? More questions. Wow. Okay. So somebody has asked something very, very advanced. Somebody has asked, what's a Fourier transform? Ziheng Shi has asked, what's a Fourier transform and how does it work? That is something which is very interesting. It needs to have more mathematics. But the good news is there's already a video about that I've made. If you go back and look at the videos earlier in this YouTube channel, you'll see a video that's about Novid, which is the app that I'm leading to try to stop the spread of COVID-19. And there's a video about the math behind Novid. In the very, very end of that video, I make some comments about how this Fourier transform type idea might work using what's called integrals, where you multiply sines and cosines by each other. So if you're curious, go there. But for this particular live stream, we're trying to keep the topic around the algebra and geometry level. What else can we do here? I see that some people are discussing how many digits of pi that they know, and I see that some people said 0. Well, I can tell you a fun question that I had to do. So I play in a contest called the National Museum of Mathematics Masters Tournament every single year. This is hosted by the National Museum of Mathematics in New York City. And what they do is they bring people who, I guess, used to play in math contests, and we get to play a math contest again. There's only one rule. No students are allowed. You know why? Because then the students would obviously win. We're not very good anymore. But I'll tell you one question that was on one of the final rounds. Maybe you guys will have fun with this one. The question was, what are the first 3 digits of pi? In base 8. Now it's not easy anymore. The first 3 digits of pi in base 8. What does base 8 mean? So first of all, let's talk a little bit about what base 8 might mean. Oh, I see that people are now like, oh boy, what is it? So I saw lots of these 3.14s, and then now I saw like 3.1 and 2.78 and 3.0, or what is the answer? Well, let's first talk about what base 8 means. So that's going to be the question we're moving towards. But let's first talk about base 8. In base 8, you might write numbers like this, like 1, 2, 7. And you put a little 8 down there to mean that it's in base 8. Now, what does that mean? If you want to convert this into normal base 10, what you do is you say, in base 8, each digit has a place value. So, for example, the value of this is these are each worth 1. In base 10, each of these are worth 10. But in base 8, each of those is worth 8. And in base 10, those are called hundreds. They would be worth 100, 100. But in base 8, each of those is worth 8 squared. The way that all of these bases work is that each additional position you go away from the decimal point, how much it's worth multiplies by 8. So that's worth 64. So if I wanted to convert this into base 10, what I would say is this is equal to 1 64 plus 2 8s plus 7 1s. Maybe somebody here is fast and can figure out what this is. Maybe I'll be a little bit slow and also try to figure out what this is. That's 64. That's 16. 64 plus 16 is a nice number. That's just 80. Oh, good. So it's 87. And these are just normal numbers in base 10. Wow, you guys are so fast. I can see that Jianhua Xing already put 87 down. But you put the little 8 here if you're in base 8. Otherwise, you don't need to put anything because that's how we normally write our numbers. Okay, but then what happens if you do decimals? Does anyone know what you do in decimals in base 8? Suppose instead of 127.8, I wrote something else. Suppose I wrote 127.15 in base. Oh, actually, I'm going to have some fun. I'm going to write 0.4 in base 8. Does anyone know what this is? So all I've done is I've taken 127 in base 8, and I have a decimal point. Well, now I see that Grace Yan is talking about the negative powers, or the fact that I take 1 over some things. You see, because this was the ones digit, and so this, if I keep using the pattern where I divide by 8 as I go in this direction, those are worth 1/8. Oh, that's nice. This is a nice number. What is 4 1/8? Well, that's half. So in fact, this is equal to 87.5. Did that make sense to people? So the bottom line is that when you take 0.4 in base 8, that's like 0.5 in base 10. And that sort of makes sense because 4 is half of 8, 5 is half of 10. And if I do this, you could do this with more digits as well. If I wanted to go and say, oh, let's try another one. If I had 127.42, what could this possibly mean? Sorry, this is in base 8. What this would mean is it's our 87 that we had before, plus, remember that each of these is worth 1/8, and each of these is worth 1 over 64 now. Because you just keep dividing by 8 every time you go in the place value this way. So now it's not 87.5 anymore. It's 87 plus 4 over 8 plus 2 over 64. And what is that? I don't really know. I'm not going to write it as a decimal because you can write it as a fraction too. Let's put the whole thing over 32s. I'm going to write a mixed number, sorry. The whole thing over 32s. The reason I'm using over 32s is because 2 over 64 is nice. It's 1 over 32. And if I want 4/8 in 30 seconds, it's 16 30-seconds. So this looks like it is 87 and 17 over 32. Okay, so that was base 8 for you. For base 8, we can get not negative numbers. We can get fractions and decimals as well. So now I hope that people understand what base 8 is about. Oh, and somebody already put down, what these things are as decimals, which is not bad. But now, what if I go back to the original question? The original question was, how do you write pi in base 8? Oh no. How would you do this? Let's let people think a little bit. Actually, this was a question that got a lot of people out. So in this particular contest, the National Museum of Mathematics Masters round, the way it works is first all of us, non-students who are much slower than you, sit down and do some problems with pencil and paper. The problems are like AMC or Amy level. Then after we're done, the top people are brought up onto the stage. And it's not like the math counts countdown round where it's two people, one against the other. No, it's like a free-for-all. Every single person's on the stage, and the announcer reads off a question, and everyone has to do the question. They're not trying to see who's faster than the other person, just who can do it. But the moment you do one wrong, you're eliminated, and then you're just like off the stage. So this particular question eliminated tons and tons of people. How would you do this? So let's start by saying, what should that first digit be? If I want pi in base 8, and I want to know up to 2 digits, there'll be a decimal point, and these two. How would you even do this? What should go here? Let's start there. What do you think? Should it be 5? Should it be 1? Well, it should be 3 over here. The reason it should be 3 is because, you see, in base 8, if it's 3 point whatever, blah, 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 in base 10, there'll be a number that's between 3 and 4. See, this part that's on this side of the decimal point, this is like the integer part, the whole number part of your number. And so, in fact, when you convert to base 8, you just need to sort of take the decimal part separately from the non-decimal part. Okay? I see some people have some answers already, which is pretty interesting. So this part is a 3. But now the question is, what's left? So I see that some people might have been doing something. Time WW Brody asked, "Did you win?" Actually, I did. But anyway, that's a separate story. But let's go back here. So it's like the rest of the stuff is like 3.14, right? So what's left? 0.14. Okay, so if there's 3 already taken here, I need to know, how do I try to write 0.14 in base 8? So normal 0.14 in base 10 as base 8? Well, the way you think about this is base 8 is sort of something where you're like, well, is it 3.0 something? Or is it 3.1 something? Or 3.2 something? Every single additional thing you put here gives you another 1/8. You can almost think of it like a ruler. Actually, that's probably the best way to think of this. So if you have like a ruler, rulers have half inches, eighths of inches, and so on. Effectively, what we're trying to do is we're trying to say, from this side, take 1/8. Am I still less than pi? If so, great. How about 2/8? Is it less than pi? If so, great, I'll use 2. And I keep going until I overshoot. I could even draw it sort of like a number line, right? Suppose I drew a number line here. And somewhere there's 3. And then somewhere there's actually pi. And what you're doing is you're trying to say, okay, how about 3 and 1/8? Where is that? I think that's around here. So this is 3 and 1/8. And where's 3 and 2/8? By the way, as decimals, this is 3.125. That's how I know it's there. And the second one is, well, there's another one here, 3 and 2/8. That's 3 1/4, 3.25. Does this make sense to people? That's why I say it's going to be 3.1 something, because if I did 3.2 something, I'm already here and going forward, and that's too big. There's no more pi. So I need to do 3.1 something. If I do 3.1 something, now I'm almost there. Now I just need to know what happens here. Okay, I see some people have some good answers already, but I need to know how much is left. And so how much is left between 3.125 and 3.14? Well, this thing here is 3.14. If I need to know how much is left between 3.125 and 3.14, I could subtract. And let's try. 3.140 minus 3.125 minus, so that gives you a 510. Okay, 0.015. And now the next question is, how much can I put on there too? So is there another digit? So is it going to be 3.10 or 3.12 or 3.13 or 3.14? Let's find out. Well, there's this gap here, which is 0.015. And now what I need to know is I'm going to be adding 1 over 64. That's how much this is worth. So how many 64ths do I put here? There are two ways to do this. One way to do this is to calculate 1 over 64 and try to divide this by those 1/64ths. If you calculate 1 over 64, it's a big mess. But if you think about what I just said, you want to take this number, 0.015. I want to take 0.015, and I want to divide it by 1 over 64. And what I'm trying to do after that is I want to know what's the whole number part. You know, the answer might be like something, point something, something of these 1 over 64s. I want the whole number part. Look at that. I don't need to calculate 1 over 64. Because if I'm going to divide by 1 over 64, what am I actually doing? I'm multiplying. So this is just going to be 0.015 times 64. What's 0.015 times 64? What's the easiest way to do this? I could do long multiplication. Or I could use the fact that multiplying by 64 does a bunch of doubling. Let's do the first doubling. That would be 0.015 times 2 is 0.03 and then times 32. You see? So I just have a 0.03 times 32. If that's the case, then this is going to give me something nice. This is going to be 0.96. I should have said, the question didn't ask what are the first digits of pi in base 8. The question was, if you write pi in base 8 rounded to the nearest hundredth, what is it? Okay? So the question was, pi in base 8 rounded to the nearest, actually it's not the nearest hundredth, it's rounded to the nearest 64th. What is it? And so when I look at this, it's like, well, it looks like it's almost exactly 1 over 64. So in fact, rounded to the nearest 64th, I saw the answers already. 1. Because I need to have about 1/64th. And in fact, if you calculate what 1 over 64 is, it's a number that's very, very close to 0.015. And so that's 3.11. Okay, so this is the way to solve this question, except that there's an even better way. So this way of solving the question, if you can see, had a lot of this like calculation and easy to make a mistake. And that's why a lot of people got eliminated in this round. There's a much better way. Does anyone know anything else that I can use to approximate pi with? And if you watched enough of my live streams, you know that I don't even like 3.14. What else could I use to approximate pi? Does anyone know? I don't want 3.14. 22 over 7. That is 3 1/7. Does anyone know what is 3 1/7 in base 8? So before I convert that, I'm going to ask you a very different question. Does anyone know what is 3 1/9 as a decimal? 3 1/9 as a normal decimal. That's nice. In fact, 3 1/9 as a decimal is 3.111111. Repeating. And I cannot go deeply into this here. That takes longer to explain properly. That actually also happens to be in our online, I believe it's one of the algebra courses. But, you know, like 3.111111. Very nice. And in fact, if you take anything over 9 in base 10 as a decimal, like 3 2/9 as a decimal, that's equal to 3.2222. And that's as base 10. So decimal is base 10. 10. 9. So it turns out that if I want to convert 3 1/7 into base 8, the base 10, compared to the denominator that I'm playing with, plays a big role. If I want to convert this into base 8, it's actually just 3.11111 in base 8. This is amazing. The reason why that's true is it's related to what's called a geometric series. It's related to the fact that 0.999999 repeating is exactly equal to 1. And if I look at this, you know what? Actually, I can explain to you immediately why this works. You see this 3.11111 in base 8? Do you know what happens if I take 0.111111 and multiply it by 7 in base 8? Yes, this is wow. This one deserves a wow. This saves all the time. The thing we just did was a horrible nightmare of lots of decimals, dividing, multiplying, subtracting, adding. We are just going to go boom, and it's over, right? Because there's something nice about 0.111111 in base 8. Look. If I write 0.11111 going forever in base 8, let's call it x. What's 7x? It will be 0.7777 in base 8. What's 0.777777 in base 8? It's the same thing as 0.999999 in base 10, because in base 8 you don't get any numbers bigger than 7. That's 1. So in fact, 1/7 in base 8 is 0.111111. 1/12 in base 13 is 0.111111. And it all works like this. So in fact, you could do the whole problem immediately. It's 22 over 7. That's 3 and 1/7. So that's 3.11. Done. Okay. You guys asked me this question of how many digits of pi do I know? That's what I thought of maybe talking to you about. But this was a legitimate, real math contest question. Of course, there was no real prize. It was just for fun. Okay, what else can we do? Ellen Wei asks, will this live stream still be a thing after the coronavirus? I don't know. The way that I decide what I do with my time is entirely based on what will help the most people. I just look at this number right here and I go and make my decisions. So right now we have 230, looks pretty good. It would be very interesting to see more though. The scales that I'm interested in trying to help are with a few more digits. So will it continue to be a thing? I'm not sure. It will all depend on how my own time is. But I'm very happy to have had this chance to talk to you, and I'll try to do this as long as I can. More questions. Oh, that's cute. So we're talking about decimals now. So Ziheng Shi asks, what is the fraction for a decimal that's going point? Oh wow, this is a crazy decimal. 0.123456789876543 repeating. So I've been asked, what is the fraction for this? Actually, that's not what the person said. The person didn't tell me this repeating. The person told me 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2. I ran out of space. Okay, I used some colors though. By using these colors, it's clear that this is a repeating decimal. And in fact, Ziheng Shi asked, that person said, this is a fraction, but what? I mean, it's going to be a fraction because in fact, everything which has a repeating decimal is always a fraction. And Tarek says, it's easy. So it turns out to be very easy. It turns out that the answer as a fraction is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, 7, 6, 5, 4, 3, 2 divided by as many 9s as I need to make that entire repeating pattern. Okay? So I'll just write a 9 under every single digit. 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9, 9. We're done. That's it. And this is a nice fact about repeating decimals and fractions. You can always just take, if you have something 0 point and then a thing that repeats and repeats and repeats, you just divide by that many 9s. The reason for this is something called geometric series. It may be a bit longer than what we want to talk about in this particular live stream, but it's really nifty. And if you test it with like something over 9, it works. If you test it for something over 99, it works. And in fact, the reason why it works is quite similar to the idea I said at the very end just now about why 1 over 7 in base 8 is just 0.1111111 and so on. Okay, so that even though this question looked horrible, it was like, wow, look at all of these digits. It was actually not that hard because of the fact that we can use math to simplify. What else can we do? Alison Wang asks, what time does this end? This is going to end at Eastern Time, 5 o'clock p.m., which is in approximately 23 minutes. What do we have here? Ranjana Jha asked, please, sir, tell me how I can be strong at trigonometry. All you have to do is understand what the definitions are. In trigonometry, there's something called sine, cosine, and tangent. And you just want to understand what those definitions are and then think about them. Trigonometry, many of you are not learning trigonometry right now, but it looks like it has lots and lots of letters and lots of things to memorize. It doesn't. It actually you just need to understand deeply what they do and play with questions that involve trigonometry, and soon you'll start to understand for yourself why each of those facts is true. Another thing is whenever you're learning trigonometry, think about why anything that someone tells you is true. Oh, I see. Somebody asked, what about cosecant? Well, cosecant is just 1 over sine. Actually, you might say tangent is just sine over cosine. Oh, and you might say cosine is just related to sine by shifting by plus or minus 90 degrees. So in fact, there's really only one function. It's called sine. But in any case, the important thing is just to understand what all of these are about and then to reason between them. If you try to memorize your way through trigonometry, it's going to be very hard. And so the answer to how to be strong is whenever you learn something, try to understand why it's true. I won't go deeper into trigonometry here though, only because of the fact that we have a different audience. Toady Master, me when I am learning trigonometry. So I think that the main thing is a lot of people unfortunately go through learning trigonometry by doing lots of memorization. Even I did at the beginning. Oh, interesting. Andrew Chow asked, what is 0 plus 0 plus 0 plus 0 plus 0 infinitely many times? Well, the answer is interesting. The answer is how can you define what the answer is? Under some ways of thinking about this, the answer is actually 0. And the reason that is 0 is because, you see, in math, if you write all these ... dots, the only question is, can you assign a meaning to that? If you can find a way to assign a meaning to something that you write down, and that meaning is consistent, then you can go ahead and say, yes, every time I write this thing down like this, it satisfies the meaning and I'm okay. What is the meaning though? So whenever I'm adding up things, if I'm adding up things and all the things happen to be positive, there is a way I can come up with a meaning for the answer. And that way, this is something you learn later in college, that way is to say, if I can find a number, some number, which is bigger than any finite sum of these numbers, then I could consider that number to be at least as big as the sum. So what I'm saying is, look, I have infinitely many things I'm adding up. But it turns out that 0 is bigger or equal to the sum of any finite number of them. And so, in fact, this infinite sum is sort of like saying, I want to add all this stuff together, but let's just consider all the finite sums that I could get from it. And if I look at all the different finite sums I could get from it, well, how high do they go? And I'll just take something which is like, my answer is, well, whatever is the height that they go. And so I could define that to be 0. Why I said that it involves them all being positive is because there are some weird things that can happen if you try to change the way that the order in which you add numbers. Maybe I'll give you an example. Watch. So this is what happens if you have both positives and negatives. Can anyone tell me what this is? Oops, I already made a mistake. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. What is this? What do you think? Well, when you look at this, there are a few natural answers that you could come up with, because you see it. I see. Somebody already said 1. Of course, because look, watch. I'll show you that this is 1. The reason this is 1 is because you just take these guys and they cancel. You take these guys and they cancel. You take these guys and they cancel, and you just keep going forever, and they all cancel. So you just get 1. So the answer is 1. Oh, but some people don't like that. Some people like to say, no. The answer is 0. The reason it's 0 is because, watch, you take those. So then the answer is 0. Which one? Well, this is a bit of a problem. Tiger Lee says it is 1/2, because why not, right? It's like it's either 0 or 1, so let's just declare it to be 1/2. What is even the answer? Well, you see, I'll show you something that's even more weird. Do you guys believe that if I add up some numbers, I can add them up in any order that I want? Seems quite reasonable, right? If I want to add up 1 plus 2 plus 3, I can first add up 1 plus 3 and then add 2. So I have another way to add these up. Watch. I want to do 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 minus 1. I'm writing a bunch of these terms, okay? And it goes on. Here's how I want to add them up. So first of all, I'm going to go and take 2 of these positive ones and add them together. So the first thing I'll do is I'll sort of add those 2 first, okay? So that gives me 2. And then once I have those 2, then I think I want to then add the minus 1 over here. I'm just doing a weird order, okay? So I'm going to write down what I've been doing. So what I've been doing is I'll take those 2 that I've gotten in green first. So I've gotten the 1 and the other 1. And then finally I'm going to add the negative 1 from the pink. Now that I'm done with that, I'm going to go and say, I'm going to now add up this one over here, okay? And also this one over there. So that's going to give me 1 and 1. And then I'll subtract off this one over here, minus 1. And what I'm always going to do is I'm always going to go and add 2 positive things and subtract 1 negative thing. Now, I will eventually get to every number, right? So I'm going to always add up 2 positive things and then 1 negative thing. And then 2 positive things and then 1 negative thing. And 2 more positive things and 1 negative thing. Now, you might say that seems really dumb. Like, why in the world are you adding like that? Can't you come up with a better idea? Well, but maybe I felt like it. I just want to add up those positive ones and then those negative ones. Because normally when you add things up, you can add them in any order, right? That's how it normally is. And I'll eventually add everything. Like, if you go and tell me, when are you going to actually add the number at the 10 billionth position? I'll add it eventually. Because eventually I'll get that. If it's a positive, I'll get it, like, eventually. If it's a negative, I'll get it eventually. So I actually get every number eventually. Oh. But if I do this, what's happening? Plus, plus, minus, plus, plus, minus, plus, plus, minus, plus, plus, minus. If you start adding this all up, it looks like it's positive infinity. So now it's not even 0 or 1 or 1/2. I could even get positive infinity by saying, I just feel like adding up my numbers in a way where I eventually add up every number, but in a weird order. But guess what? I can also do this negatives. I see that somebody else has also commented that I need a haircut. This is true. In COVID-19, I think we all need haircuts. I'm not entirely sure when we're going to get haircuts. At some point, everyone's going to have to learn how to give themselves a haircut. Okay, let's keep going. If I want to go and get negative infinity, how do I do that? I can do that too. 1 minus 1 plus 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 1 minus 1 dot dot dot. Now what do? I just do the opposite. I will first take the negative and the negative, add them together, minus 1 minus 1, and then add 1 positive, plus 1, and then more negatives, minus 1 and minus 1, minus 1, minus 1, and then take a positive again, plus 1, and you go, and you go, and you go. And if you do all of this, eventually you'll get every number, because eventually you'll have added every negative thing. You'll have gotten there somehow. You'll also have gotten to every positive thing somehow. And your answer is going to be minus infinity. So at this point, what this is showing you is you can get all kinds of weird things. You can get 0, you can get 1, you can get plus infinity, you can get minus infinity. In fact, you can even go and get other weird numbers in between if you just are clever about how you choose what you want to add and what you want to subtract and when. So unfortunately, you can't have a nice way of adding all of this up. You can, if you want, define that I have something called a limit where I take the sequence and I just go and say, if I add up every element of the sequence and I just go in order, does that converge to something? You could do that. And indeed, in this case, the answer would be it does not converge. But I wanted to use this example to show that the commutativity of addition, if you put dot dot dots, it even becomes really weird. There is one nice thing though. If you're adding up numbers and they're all positive or they're all bigger or equal 0, then you can add them in any way that you want. And that's why in that particular case you gave me of 0 plus 0 plus 0 plus 0, that one, under most mathematical definitions, you would go and use conventions. You'd use that it is just plain 0. Okay, what else can we do here? Oh, you found an infinity emoji. I see a lot of people ask, can I teach the normal distribution? I believe we talked about that actually in one of our earlier live streams, and we just talked about how there's this curve which you can use that a lot of things that we measure in the world converge to. So I think we already covered that, so we're not going to hit that today, unfortunately. But do keep watching us, because what you'll find out is if you watch this live stream for a while, we'll have touched lots and lots of different math topics. Euler's identity we actually also talked about in an early live stream, so I'm afraid I won't be able to hit that one again. Did you hear a noise? I did hear a noise. The noise was maybe me bumping against the computer like this. Occasionally there are noises like this that happen. How does Minecraft randomize biomes? We did touch on this on an earlier live stream also, but my gut feeling is they go and come up with a mathematical model that will say like, how tall should the ground be? Should there be water here? And you go and you mess with what we call parameters, which is like how mountainous do you want the area to be? What's the probability you want a mineral to be somewhere? And you can find out that with not that many parameters, not that many choices of these numbers that you set, you can say generate, and then you get something that looks pretty interesting. In fact, that's how the world works too. In some sense, the whole of nature is generated by a small amount of information, like the DNA or the RNA that is used to make an organism or a virus. Let's see. What else do we have here? Time WW Brody asks, how many competitions should I focus on per year? As many as you can find. I don't think that there's really an upper limit. In fact, I think that if there's any competition and you have the time to do it, go for it. In this particular time of, well, not this particular time, but in this particular climate, this particular moment where we're not able to go to schools physically, I would say there are probably even more of these online competitions that you can join. So I'd recommend just join all the ones that you can. It's always good to be doing something which is challenging. And to me, what's special about a competition is it's by definition challenging, right? It's like the difference between your homework problem, which comes from a textbook, and a competition problem, which doesn't come from a textbook, is that the author of the competition problem is somebody who wanted to think of like something that might be a little bit interesting that you might have to invent some way to do. So there's never, you'll never run out of doing, sorry, not that you'll never run out. You'll never be in a problem where you're doing too many competitions. LMT. Oh yes, David Jiang asks about the LMT. To me, that's the Lexington Math Tournament. I, in fact, don't know what's going to happen with that, but judging from the fact that it's run by high school students, I wouldn't be surprised if the high school students try to run something from Lexington High School that will let even more people participate. In fact, actually many students right now, all over the world, are in a situation where you have a little bit more free time or flexibility to try to think about what you can do. I know that it's also quite boring. I mean, somehow it's no fun to be able to not be able to go to school, to not be able to see people. So a lot of people are stuck at home, quite bored. And so these kinds of competitions that people can use their energy to try to organize are things that people choose to do. So I even am saying that because if you are bored at home, if you can find a bunch of people to create something with, then you suddenly won't be bored anymore. And suddenly you'll say, good gracious, I don't have enough time to do everything I want to do. I see PyMage1415 has asked, is Novid out? Well, we've submitted it to Google. Google is thinking about it. And right before this live stream, and actually the reason why I was late is because we were preparing a submission to Apple. So we hopefully, as soon as this live stream finishes, we'll go back to filming a little video that we needed to send to Apple to explain, what is this app doing. That's what we're up to right now in this office. Okay, and will Novid be on iOS? That is the version that we're building right now. Building in the sense that we're putting the finishing touches on it, and we are putting a version that we're going to send to Apple, hopefully today. Okay, but when I say today, that doesn't mean that you'll get it today. That means that then Apple has to go and think about it, and they will have to go and decide whether or not this is something that they believe that the global public can use. Okay. I see. So I'm just looking at all of these different questions to go and try to see, is there something that I can use that would be an interesting thing that we can use? Oh yeah, let's do that. Temp ID says, talk about RGB color coding. And the reason I think that would be a nice thing for us to talk about today is because we already were talking about base 8. So there's something that you see in computers. If you ever do computer programming or computer graphics, you will often see something like this. Red. Oh, you know what? I have a better idea. Red. I'll just write it in red. How many people have seen something like this before? And in fact, I'm going to say that this is not quite FF0000. I think that the more appropriate way to describe what I just did is it's probably more like FF00, maybe AA. What in the world am I talking about? So now this is 6 things long, and those things in the middle, those are not O's, those are zeros. And we're talking about hexadecimals, hexadecimal notation. And they also, this person said, it's called RGB color coding. This part is R. R stands for red. This part is the G part. It stands for green. And this part is the blue part. B. B stands for blue. And it turns out that colors are made out of red and green and blue if you're thinking of light. So if you think about colors that you paint, like the paint that you use is usually red, yellow, and blue. That's because that's something called subtractive colors instead of additive colors. But when you go and make light, if you go and take a red light, a green light, and a blue light, you might have seen these pictures before where they kind of all join, and where they intersect, you get all these interesting colors. Like where the red is and the blue is, you get something that looks sort of like this shade. And where the blue is and the green is, you get yellow. And where the green is and the, when the blue and the green is, you get some like cyan, it's like blue-green. And where the green and the red is, that's where you get yellow. And then somehow right in the middle, what you see is white. And somebody asked, what about CMY? That's cyan, magenta, and yellow. Those are related to printing. So there's a difference between light colors and colors that you print as ink on paper. Light is something that goes directly to you. That's called additive. So if you have something that's emitting red light, green light, and blue light, your eye gets it, and it's like, oh, it's white. But when you think of what you've colored on paper, the color that you've made on paper doesn't glow at you. In fact, what it does is it takes light that comes down and it subtracts out some colors. That's called subtractive color. So like the red pigment on a paper, like if you use a red thing and draw on paper, it doesn't emit red light, it just absorbs everything else other than the red light, roughly speaking. So that's why the CMY is slightly different. I see people are already talking about the green for the green shirt. But now if I have the red, green, and the blue, the way you think of this is that there are two letters or two numbers that denote how much red, and then 2 that denote how much green, and 2 that denote how much blue. Now, how much can there be? Well, these numbers are numbers that go from 0 to 255. And the reason for 255 is because a long time ago, computers were using, well, not, they still do, but they use bytes, B-Y-T-E, and a byte is 8 bits. So a byte was used to store one character, like, like an A or an X or a minus sign or something like that. So in fact, computers store things in bytes. And what this thing does is it actually stores in 3 bytes. Each byte is each byte is 8 bits. In 3 bytes, it stores how much red, how much green, and how much blue. There's basically 1 byte for red, 1 byte for green, and 1 byte for blue. And if your byte is bigger, meaning it's closer to the maximum the byte can be, which is 255, you're putting more red. And so that was the principle. The principle was that each of those numbers is supposed to be some number from 0 to 255. So this is some number that is from 0 to 255. And that's telling you how much red there is. Meanwhile, this is some other number from 0 to 255. And this is some number from 0 to 255. And the way to think of this is 255 is like maximum. So it's sort of like if they were using base 10 instead, they would have called these out of 100. It's like, out of 100, what percent of the red light do you want to turn on? Do you want to turn it on at maximum? And here in computers, we use base 2. And so the numbers are in bytes, and so it goes up to 255. This range, 0 to 255, has exactly 256 options, which is 2 to the power 8. So ultimately, when you look at these colors, this is just telling you how bright it should be. Except that the way that we write these things down, we don't write them down as like the numbers 255. We actually write them down in base 16, hexadecimal notation. And in base 16, here's what happens. You have 2 digits in base 16, because each of those is 2 digits. And how much is each digit worth? These digits are worth 1, and these digits are worth 16. And clearly, the 2 digits that we're playing with are F and F. Oh no! What kind of a digit is F? I thought digits were 0, 1, 2, 3 up to 9. Well, they are. The problem is that if you're in base 16, you also need something to represent 10, and something to represent 11, and 12, and so on. And so, in hexadecimal, in base 16, you have the normal digits, 0 representing 0, all the way to 9 representing 9. But then something needs to represent 10, and so people use A. And B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. Aha! So that's what this is. FF. Oh, I see people already wrote this down. Thank you, Luke Wang. So if I have this, the FF, what that corresponds... Oh, wait, actually, Luke Wang was talking about something else. Luke Wang was, I think, talking about the piano keyboard. But David Xiang, yes, that's what we wanted. So FF, and that is equal to... It's 15 of the 16s plus another 15. Guess what this is? Well, if I multiply 15 times 16, that's equal to 30 times 8. That's the easiest way to multiply 15 by 16. Take a factor of 2 from the 16 and put it across, and then plus a 15. Oh, good. So this is 240 plus 15, and that's equal to 255. So in fact, FF is called maximum red. By the way, let me close this live stream with a nice trick. Yes, FF is 255. I did a lot of work to do that. Here's an easier way. If I want to know what is FF in base 16, just add 1. Also in base 16. What's this? Well, it's just like your normal addition. You're able to add numbers. I mean, the addition algorithm still works. FF plus 1. What is F plus 1? F is 15. 15 plus 1 is 16. So 16, I should write 16 down here. No, you can't do that. You have to write 1 digit. Well, where's the 16? Oh no, there isn't one. That's because 16 in base 16 is 1, 0. What you have learned in school for addition works in any base. Okay? So now 1 plus F, that happens again. F is 15 plus 1 is 16, but 16 is 1, 0. Aha. So FF plus 1 in base 16 is 100 in base 16. Well, what's that? That's 256. That's 16 squared. And this is 1, normal 1 in base 10. And so FF in base 16, and so FF in base 16 is just 1 less than 256. Boom, it's 255. And so this is like a nice trick whenever you're playing with hexadecimal. And whenever you see FF appear, you know that that's like the biggest you could have. You add 1 more and everything carries over. And it's just like 99 plus 1 is 100. Yes, that is so cool. I agree. The first time I ever saw that, I was like, wow, you're able to save so much work. And by the way, it also works if I have FE. Suppose I had FE, what would I do? FE, E is 14, Fe plus 2 is 256. So Fe is 254. Boom. Okay, so as you can see, this math is useful for all kinds of things. If you someday go and do computer programming, or if you do graphic design, you might find yourself playing with all of these kinds of things. It looks like we unfortunately have run out of time for today. That finishes our weekday live stream. As you know, on the weekend, I come with a different kind of a question, and I'll have to tell you what I'm thinking about. Basically, I go and choose some math question that's related to something I've been thinking about recently. And so that will be at 8 o'clock p.m. Eastern Time tomorrow, which is in approximately, if I could do that kind of math, I think it's in 27 hours. I hope that you all have a very happy end of your week, or beginning of your next week if it's already Saturday for you on the other side of the world. Please stay safe, and please keep thinking. And also, if you liked what you just saw, please tell other people, because that is honestly how I make my decision of whether we're going to keep doing all of these live streams. I really enjoy the chance to get to know all of you. I think that you ask really interesting questions. You make me have to think, and I find that fun too. But it will be much more worth it if we can bring even more people into this world. Until next time, I wish you a very good day, and stay safe. Good night or good morning.